In this video, I'm going to look a little bit deeper into the ideas of converting from Cartesian to polar coordinates in my double integrals. In particular, I may not see a very obvious substitution in my function. For example, I might have terms that involve x times y, or e to the negative x squared minus y squared. Just because it's not obvious that I have x squared plus y squared or something very straightforward, it doesn't mean that I won't benefit by converting to polar coordinates. I may need to spend a little time just playing with some ideas about converting it. So let's look at an example. I want to sketch the region of integration R and evaluate the integral over R using polar coordinates for each of the double integrals. In the first case, I have a double integral over the region R of e to the negative x squared minus y squared dA, where R is the region that is comprised of all points x, y, such that x squared plus y squared is less than or equal to 9. In this case, my region of integration R is a circle centered at the origin with radius of 3. I'm not going to sketch these. I'm going to assume it's possible for you to do that, but I want to identify what that region is. In the second case, I have the double integral over R of xy dA, where my R is defined to be the region of all points r theta, such that 1 is less than or equal to r, which is less than or equal to 3, and 0 is less than or equal to theta, which is less than or equal to pi halves. This region is a quarter of an annulus, which is a ring of width 2 units that is located in the first quadrant between 0 and pi halves. For part A, remember that I have a region that is a circle of radius 3, and I'm going to express both my integrand and my region now in polar coordinates. I'm going to first look at my exponent in my integrand, and I'll note that negative x squared minus y squared is the same thing as saying negative the quantity x squared plus y squared, which will be equal to negative r squared. Similarly, my region becomes the region of all points r theta, such that 0 is less than or equal to r, which is less than or equal to 3, and 0 is less than or equal to theta, which is less than or equal to 2 pi. Now I'll set up an iterated integral to represent my double integral. I want the integral from 0 to 2 pi of the integral from 0 to 3 of e to the negative r squared r dr d theta. I'm going to do the inner integral first. I get the integral from 0 to 3 of e to the negative r squared r dr. I'm going to make a substitution real quickly. I get the integral from 0 to 9 of e to the negative u over 2 du. When I do the integration piece, I get negative e to the negative u over 2 evaluated from 0 to 9, which gives me 1/2 minus e to the negative 9 over 2. This becomes the integrand in my outer integral, so that my outer integral is given by the integral 0 to 2 pi of the quantity 1/2 minus e to the negative 9 over 2 d theta. I integrate that and I get the quantity 1/2 theta minus e to the negative 9 over 2 theta evaluated from 0 to 2 pi. This becomes pi times the quantity 1 minus e to the negative 9. In B, I have the double integral over the region R of x times y dA, and my region is already in polar coordinates. It is a set of all r theta such that 1 is less than or equal to r, which is less than or equal to 3, and 0 is less than or equal to theta, which is less than or equal to pi halves. In this case, I need to use the relationships that say x is equal to r cosine theta and y is equal to r sine theta, so that x times y becomes r squared cosine theta sine theta. My iterated integral becomes the integral from 0 to pi halves of the integral from 1 to 3 of r squared cosine theta sine theta times r dr d theta. I simplify that just a little bit and I get the integral from 0 to pi halves of the integral from 1 to 3 of r cubed cosine theta sine theta dr d theta. My innermost integral is the integral from 1 to 3 of r cubed cosine theta sine theta dr, which gives me r to the 4th over 4 times the cosine of theta times the sine of theta, evaluated from 1 to 3. This gives me 80 over 4 cosine theta sine theta, or 20 cosine theta sine theta. This becomes my integrand in my outer integral, so that I'm taking the integral from 0 to pi halves of 20 cosine theta sine theta d theta. This gives me 20 times sine squared theta over 2, evaluated from 0 to pi halves. I plug in those limits and I get 10. Now I want to do another example where I'm going to compute the volume of an island that has a surface defined by the function z is equal to 20 divided by the quantity 1 plus x squared plus y squared minus 2, over which the function's non-negative. The first thing I need to understand is where my function is non-negative. It will be non-negative as long as 20 divided by the quantity 1 plus x squared plus y squared is greater than or equal to 2. When I simplify this inequality, I find that it's true when x squared plus y squared is less than or equal to 9. This gives me a region of integration that's defined by a circle centered at the origin with a radius of 3, so that my region becomes a set of all r theta, such that 0 is less than or equal to r, which is less than or equal to 3, and 0 is less than or equal to theta, which is less than or equal to 2 pi. My iterated integral becomes the integral from 0 to 2 pi of the integral from 0 to 3 of the quantity 20 over 1 plus r squared minus 2 r dr d theta, where I've simply plugged in r squared for the sum of x squared plus y squared in my original function. The innermost integral is the integral from 0 to 3 of the quantity 20 over 1 plus r squared minus 2 r dr. This integrates to 10 times the natural log of 1 plus r squared minus r squared, evaluated from 0 to 3. I plug in those limits of integration and I get 10 times the natural log of 10 minus 9. This goes into my outer integral and I get the integral from 0 to 2 pi of 10 times the natural log of 10 minus 9 d theta. I integrate that and get 10 natural log of 10 minus 9 all times theta, evaluated from 0 to 2 pi. I get 2 pi times the quantity 10 natural log of 10 minus 9. So now you get to try it. Pause the video and evaluate the integral over the given region R using polar coordinates. When you're ready, restart the video to check your understanding. You're going to be evaluating the double integral over the region R of the quantity x plus 3y dA, where my region is a set of all points r theta that give me 1 is less than or equal to r, which is less than or equal to 4, and 0 is less than or equal to theta, which is less than or equal to pi halves. For this one, my region is already in polar coordinates. This is part of an annulus region that has a width from 1 to 4 or 3, and it lies in quadrant 1 between the angles 0 and pi halves. My iterated integral becomes the integral from 0 to pi halves of the integral from 1 to 4 of the quantity r cosine theta plus 3r sine theta r dr d theta, where I've used x is equal to r cosine theta and y is equal to r sine theta to write my integrand in polar coordinates. My innermost integral is the integral from 1 to 4 of the quantity r squared cosine theta plus 3r squared sine theta dr. My integration piece gives me r cubed over 3 times cosine theta plus r cubed sine theta, evaluated from 1 to 4. Plugging in my limits of integration gives me 21 cosine theta plus 63 sine theta. This becomes the integrand in my outer integral, the integral from 0 to pi halves of the quantity 21 cosine theta plus 63 sine theta d theta. This gives me 21 sine theta minus 63 cosine theta, evaluated from 0 to pi halves. I get 21 plus 63 is equal to 84. Note that not every integral will actually become simpler when I convert it into polar coordinates. Some of them work great just as they are, but oftentimes my integration will be significantly simplified if I'm able to convert to polar coordinates. Be sure and let me know if you have any questions.